It's 12 now, so we will get started with the seminar for today. Today we are honored to have Professor Yumeng Li to visit us. Professor Li is currently an assistant professor in the Department of Industrial and Enterprise System Engineering at UIUC. She holds a PhD degree in aerospace engineering from Virginia Tech. So her primary research interest involves mechanism-driven materials and structure design, computational modeling and simulation, and physics-informed machine learning. So today she will talk about her work, and I will give the stage to Professor Yumeng Li. Let's first welcome the speaker.
Thank you. Thank you very much for the introduction. So also many thanks to the invitation. I'm also honored and so glad to have this opportunity to present some research from my group. So today, especially, I would like to introduce some work from a group regarding battery like a design of 3D-architected electrode for high performance battery. So the specific method we developed and used for the battery design is physics-informed machine learning. So I will talk about more regarding that. But before I move to that specific topic, I would like to give a very brief overview about some of the research from my group. Hopefully that can inspire some collaboration opportunities here. So first of all, I stated in Material Initiative, which is launched by US Congress in 2011, we have entered an era where predictive modeling can transform our capability to design material structures, processing process, or manufacturing process with a frictional cost and the leading time. So my group has been part of that effort to advance modeling and simulation techniques, especially multi-scale, multi-physics simulations, to deepen our understanding about complicated systems, for example, or especially materials and structures. And furthermore, we have been integrating those physics simulations with machine learning to develop high-fidelity predictive models that we can use to accelerate the discovery and design of novel materials and structures. So some of the examples, especially we have been working on lead-weight structure. So this project is supported by DOE, Department of Energy. We have been working on dissimilar material joints. So we have been working our collaborator from Penn State, Michigan, to investigate several different kind of advanced manufacturing techniques to build dissimilar material joints and understand or investigate such kind of dissimilar material joints under different service conditions. Especially for my group, we has been developing statistic predictive models to quantify their current performance under different conditions, also considering the design of the dissimilar material joints as well as the manufacturing process. So that's one thing we have been working on for smart manufacturing. We have been collaborating with some leading company in electronic assembly, trying to explore the capability using AI-enabled quality control process. So for inline quality control to replace a currently very manually done or highly subjective inspection system. So that can increase the quality of the assembly or ensure the quality of the assembly and also increase the efficiency of the manufacturing process. And recently, we just received a fund from NSF so that's kind of build on our work to develop AI-based inspection system. We get some funding from NSF to use that towards remanufacturing. So we can consider the remanufacturing in the product design space. Then that will help to design products that can be remanufactured or to increase their sustainability and resilience. One more thing I would like to talk about is nanostructure surface. So this is also supported by NSF. We have been looking at how bacteria interact with those nanofacture surface. Then we can understand the killing mechanism and use those knowledge to optimize the design of those nanofabricated surface for different applications, like for implant devices. So the last one I want to go deeper will be the battery. Especially, we're going to talk about architectured electrode. So why we are interested in battery? That's kind of a simple question. But we have battery everywhere, so we have them powered different kind of devices we use almost every day, and also such kind of large demand device. And the global trend in electrification has been, demands the batteries have even better performance. We want them to have high power density, energy density, better lifetime, cycling lifetime, as well as reliability, also like a fast charging performance. We want more, but how can we design such kind of battery? So one of the possibility or one of the promising solution is to using some new materials for the electrode. So one example is silicon. There are several different types of new anode material has been exploring. So silicon is kind of representative material of that. So for silicon anode, theoretically, they can have much larger storage capability than up to 10 times of the traditional graphite-based battery, lithium battery, and how much higher capability as well. I put some of the specific number over there. In such kind of huge improvement in the performance is due to the very special or unique intercalating, like alloying mechanism. So we can incorporate more lithium ions into the silicon crystal structure. But such kind of unique lithiation process is also leading to problems, because by bringing more the ions, they're going to induce large volume change as well in the electrode. Such kind of large volume change can lead to mechanical failure of the electrode, which two typical mechanical failure mechanisms we have been observing from experimental testing is cracking and delamination. So the cracking and delamination are the two major failure mechanisms has been observed for silicon-based anode. A lot of techniques or method has been explored to address such kind of serious mechanical failure or degradation. One of the possibility is to do some like a geometry. You adopt specific geometry in the electrode. So one of that is called 3D architecture. So we can have 3D architectured electrode to mitigate the stress induced by the lithiation during the lithiation and delithiation process. So one example is use such kind of open void 3D structure. That's one of the 3D architecture electrode has been explored recently to mitigate the volume, large volume change in silicon anodes during the lithiation or delithiation process. But how can we identify? Although current study have demonstrated it's quite useful for mitigating the stress induced by volume change during the use of silicon anodes. How can we quantitatively quantify such kind of effects and use such kind of knowledge to assist in the design of the battery? Is still need a lot of work. Besides that, if we rely purely on experimental study, that's quite expensive, and a lot of we're going to do repetitive experiments, and we need to do also we need to collect a lot of data from experiments as well to facilitate the design process. That's not very feasible. To just rely solely on experimental testing. That's why we want to develop multi-physics and multi-scale simulation models to understand, to quantify the effects of 3D architecture electrode, how that will impact the degradation process, how that will impact the lifetime performance of the battery, and use that to facilitate the design. The reason why we have to have a multi-scale simulation, that's because the performance of the electrode itself, the overall performance for the battery, for the function as a battery involve or impacted by factors from multi-length scales. So we have the 3D architecture that's at macro scale, and we have the lithiation process that's determining or governing the mechanical deformation within the electrode happening at the nanoscale. So how can we incorporate that? How can we consider all the factors from different length scales? That's why we go in the direction of multi-scale simulation. So we have macro-scale models, we have macro scales that they share information with each other. Then we can finally quantify the performance by using different kind of metrics. And the next step, after we get those multi-scale, multi-physics model or simulations developed, one critical step is how can we use such kind of knowledge? How can we use this data to facilitate the design? Although the simulations or physics-based simulations we have here is much cheaper than experimental testing, but it also carries with some cost. We cannot. We don't want to repetitively run such kind of expensive simulations over the design process. So one thing we has been trying to, we want to build a surrogate model that can replace the physics simulation. Then we can use the data generated from it to quantify the performance of the battery at different conditions. So this illustrates the general platform of the multi-scale models we developed. For the macro-scale model, the major feature we're going to carry is the 3D structure that will investigate how the 3D structure impacts the stress distribution within the electrode under different operation conditions, like temperature, charging rate, And with that information collected, we can pass to the macro scale model. So for macro scale model, we have a rather simplified we use a rather simplified representative volume model, which is kind of a thin, only one thin layer of silicon on top of the substrate. The substrate will usually be metal. The main feature we're trying to capture in macro scale model is one comes from the material microstructure. So how the silicon is deposited on the substrate, the microstructure can be impacted by the deposition process. So the microstructure model can capture the effects of that. In addition to that, we can investigate the failure, the mechanical failure process, how the cracking and delamination is happening within the thickness direction of the silicon layer. Use that information. We can extract the features and capture the damage level, damage failure, and impart that to the electrochemistry model. Using the electrochemical model, we can quantify the degradation performance over time under different operation conditions. So at the macro scale, so it's the main model will be solid mechanics model, which we are mainly interested in the stress distribution that's changing with the architecture. And then we can quantify the stress level and also the stress history over the charging process. Then we can use as input to our macro scale level, which is I want to go more into details about. So at the macro scale model, also we have two models. Right now it's one-way coupling. We have the solid mechanics model for capturing the cracking and delamination. With that quantified, we can pass that to electrochemical model, then to quantify the electrochemical degradation, mainly due to the formation of SEI layer. So the SEI layer is one of the dominating or major failure mechanism that can consume the electrolyte and also increase the resistance of the electrode that can change the transportation of the ions within the electrodes. That's kind of the major mechanism we want captured in our electrochemistry model to and use that to quantify the performance of the battery. So for the macromechanics model, so if we think about the battery, the operation of it, the lithiation process, the delithiation process with the mechanical failure, the cracking and delamination, they all couple together. But it will be very expensive or sometimes impossible to simultaneously simulate that in a model, in a single model. Based on our observation, the cracking and delamination that create what we call islands, the silicon islands within the thickness direction of the silicon anode in very first few cycles. After that, they won't change that much. So that's why we think it's reasonable to separate into one. First of all, we use solid mechanics model to quantify the size of the silicon island, how the silicon islands change with the design of the electrode, including the architecture, the thickness, also the microstructure within the silicon layer. After we get that information, we can pass that to our electrochemistry model. And first of all, in this case, for the solid mechanics model, we have one thin layer of silicon deposits on nickel in this case. So in order to allow the simulation of the cracking and the delamination, which is the detachment of the silicon layer from the nickel base, we need to have a way for those cracking to be simulated in finite element. So one way we have been trying to use cohesive zone elements. So we have the microstructure. So in this case, we simulate it as a polycrystal microstructure. We have the different grains. We have the grains, have the grain boundaries. The grain boundaries have a different mechanical property as the within grain silicon, and that kind of mechanical property will be buried or carried within the cohesive zone laws we use here. In addition to that, cohesive zone element also placed between the silicon and the nickel that's captured the adhesive, how the silicon material, how it's adhesive to the nickel base. That's also can impact by different kind of parameters as well. But such kind of adhesive strengths also be the parameter to quantify such kind of strengths will be carried within the cohesive zone law as well to simulate the behavior of the cohesive zone element. By having such kind of model, we are able to, first of all, look at how the cracking is propagating between the grain boundary, and also how much delamination can happen between the silicon and the nickel base. And one more important thing is, this is much simplified. Doesn't have any curvature captured in our macro scale level, but how can we consider the 3D structure of the electrode in the first phase? How to include that influence here is the stress field that's simulated from the macro scale level. The stress field information, the magnitude of it will be used as a boundary condition. So this macro scale level will experience the stress history that we calculate from the macro scale level. For the electrochemistry model, that's mainly capturing the major mechanism, failure mechanism that's trying to capture from this model is the SEI layer growth. So for SEI layer growth, that will happen on the surface between whenever the surface, we have the surface exposed, or the surface of the electrode exposed to electrolyte. So such kind of surface or how the size of such kind of surface will be determined by the mechanical failure. So whenever we have a crack, or whenever we have a delamination, we're going to have new surface created that can be, that's where we can have SEI growth that will induce the battery degradation. So for electrochemistry model, this model is just trying to use certain governing equations to simulate the transport of Li ions between the cathode and anode under different operating conditions like charging rate and temperature, how such kind of, how the process, during the process, how the SEI grows. Then the major parameter or major feature we want to quantify in this simulation is the thickness of the SEI layer, because that's proportional, highly proportional with the degradation. So if we look at the results from the solid mechanics model at the macro scale level. We can look at the stress distribution, and also we can identify the island size that's created. In addition to that, we can quantify the delamination damage by looking at the exposed surface that's created due to delamination. So what we did is we look at the different type of case we have. We vary the thickness of silicon on the nickel base. With increasing of the thickness of silicon, we can observing the changing of the larger silicon anode island, and with that kind of information gathered, we are able to say to determine the representative volume element for the following electrochemistry model, where we can capture the degradation process. So the degradation process, one of the parameters we are using to quantify the degradation of the process is what we use relative capacity loss. So it's always start with 100 and changing over the cycle lifetime. So here, those are the major parameters we're including our multi-scale simulation. We can understand, we can do sensitivity studies to look at how those different factors either come from the design of the anode or the operation conditions of the anode, how that will collectively impact the lifetime of the 3D architectured silicon anode. So basically, for the temperature case, if we increase the temperature, there will be much faster degradation. So that also means the thermal management can be very critical to the performance of the battery. For the charging, the 2C, 1C, and 0.5C, that's representing the charging rate. So 2C, I think that's mainly mean 2 hour. No, that's not 2 hours, that's inverse. So 0.5C is the slowest charging, and 2C is the most fast charging. So if we increase the charging rate, that's also induce further degradation of the electrode. The last one is the thickness of the silicon as well. So that's kind of the design parameter we can control for the 3D architectured electrode here. So with with all those data collected, we have all the parameters either from temperature, charging rate, or structure design. The thickness mainly in this case. We haven't moved on to integrate the features from the 3D structure yet. That's something we're working on right now, but that's definitely something very interesting to look in. And more importantly, we need to validate our model. So luckily, we got some experimental data from our collaborator at the USC. They quantify the performance of the silicon anode with different thickness at different temperature, as well as different charging rate. So here I only present 3 examples. That's for the same thickness, the same temperature, but different charging rates. But we do have more results that have a better comparison between the experimental testing with our simulation results. This kind of help us to understand how valid our model is. When it's low charging rate, like 0.5C and 1C, we have a relative good performance. But for the 2C case, the experimental testing kind of underestimate That's probably due to the simplified model, some assumption made. We are looking into more details. How can we further improve the performance or fidelity of the predictive model? So next step, now we have our multi-scale, multi-physics simulation, and we have that to validate to a certain level. So we have some confidence we can move further to generate data that can be used to get our design. But how we, one critical step is we need to bridge the gap between physics simulation with the optimization design process. We need a large amount of data for design, but the multi-scale simulation is quite time-consuming. So that's when we bring in the surrogate model. For this case, that's a pretty simple surrogate model we used is a Gaussian process. It's kind of enough for us for this case. So we have the Gaussian process model that's developed based on the data from the simulation. And this table is mainly to illustrate with the input of cycle number, thickness, charging rate, and temperature. We can predict the relative degradation, relative capacity of the battery. So that means for this surrogate model, we can have some design parameter. We have operation conditions. Also, we can predict the history of the degradation process as well. So right now, the surrogate model, the fidelity of it seems pretty well. We are happy with that, at least for right now, the current stage. If we plot out that, we can view the change of the capacity loss at a certain cycle life that's changing with those parameters we included in our model. So this is just one way to show we can capture the performance surface over those design space, and such kind of surrogate model will provide a base for future analysis. So for the first study we did is we can do uncertainty quantification with some initial analysis or initial assumption regarding the distribution of the input parameters, like the thickness and operation conditions. We can predict the distribution of the performance that's the distribution of the performance regarding each of the individual parameter or the collective collective influence of those all parameters. And among that, we can identify which parameter is most critical in terms of the reliability of the battery, in terms of the reliability performance of the battery. And another thing we did is the Gaussian process model we developed can be also used for battery health assessment and monitoring as well. So with that Gaussian process, we can generate the voltage curves that's changing with not only design, also that's changing with that show the sign of failure happening. So for a simple case is here we only plot out two charging rates at different temperature. So with the increasing of cycle life, we're going to observe an increase of voltage there. That's associated with increase of resistance due to the forming of ICI layer. In addition to that, if we map out all the voltage curves for different scenarios, we can provide a reference or a data bank that we can compare once we get some health assessment using experiment testing, and that kind of characterization can be just a single voltage segment. So if we have a segment that's showing the change of the voltage over a certain time, we can use that to compare with the voltage curve we generate based on our model, then identify the current health state of the battery. So such kind of function of the Gaussian process provide a relatively simple way for us to estimate. Without doing destructive testing, we can have a quick assessment of the current health state of the battery. That can be used for maintenance or operation management, or even recycling of the battery, because at the end of life, we need to know what's the current health stage of the battery in order to think about if we want to use to let the battery have the second life or not. So build on that, we have been trying to extend our research into different aspects regarding the battery study. So one of the study we did is, so right now the Gaussian process model is built only on simulation data because that's relatively expensive to gather experimental data. But if we have experimental data, we definitely don't want to throw it away. We want to leverage that. By incorporating the data from different sources, the main challenge associated with that, we can have different output. Like the performance evaluation come from simulation can be different from the experimental testing because the limitation of experimental testing, how frequent you can test it, what kind of property you can test it. Experimental testing can have a lot of limitations. So we can have different data that have different formats. And if we want to combine that, we're going to have what we call partially observed data. So simulation can have a full data set comparing to experimental data, which only have part of the inputs that have been observed during the testing process. If we combine that, we need to address this, what we call partially observed data problem in our simulation. In the development of the surrogate model. So that's why we introduced this model, the latent variable model, then inversely calculate the missing input parameters that's needed for the training of the surrogate model. Then we can build a high-performance surrogate model that's leverage all the data from different sources. In addition to that, we have been trying to extend our model to include thermal effects or thermal performance of the battery. So this is one of the efforts we have been doing to do a co-design of the thermal management of the battery pack. First of all, we can have a finite element simulation to simulate the thermal distribution within the battery pack, especially under dielectric immersing cooling environment, because such kind of cooling techniques has demonstrated is quite useful for battery pack thermal management. By integrating the simulations we've done And such kind of simulation can create data for surrogate models. We can use those surrogate models for the design that's considering not only the battery pack, like the arrangement of the battery, as well as the control system about the cooling, like the inlet velocity. Mainly, right now it's mainly the inlet and outlet velocity of the cooling liquid. So we can see how the performance changing with different package pack, battery pack, and different cooling strategy. So for the summary, I don't have a lot to talk, not involve a lot of technical details, but based on all the study which has been done, or mainly research in my group has been focusing on exploring how to integrate physics into simulation to develop surrogate models for high-fidelity predictive model we can use for the design. Especially the application will be materials, battery systems, or structures. And we has been, so the current study has demonstrated such kind of predict models based on the physics-informed machine learning can be quite useful in different aspects of the battery, either reliability-based battery design, manufacturing, like how you control the 3D structure of the electrode. That's some. We also published some work on investigating the uncertainty associated with the 3D structure, how that will impact the performance of the battery. Health monitoring management. So that's basically we're trying to show the capability of those physics-informed machine learning. And last is acknowledgement to my PhD students. Our credits go to them, and also thanks all our sponsors as well. Yeah, I think that's all I would like to talk about today. So if you have any questions, I'm more than happy to answer that. Thank you.
One quick question I have is in your multi-scale, multi-physics model, do you consider the manufacturing variation in the battery?
So right now, currently, I think the macro scale model, like the macrostructure, the features of macrostructure, like the grain distribution, grain size distribution, the grain boundary properties, that can be determined by the manufacturing process. And at the macro scale level, like the 3D architecture, the geometry of that, the uncertainty associated with the geometry creation by the manufacturing process also can have influence on the performance of the battery and the life cycle performance as well as the battery. I think that's right now we haven't go up to macro scale level to investigate, directly establish the relationship between the feature of 3D structure impacted by the manufacturer process, relate that to the performance. But right now we are able to relate the macro structure level, like the macro structure features, to their performance. That's yes. So we hope we can go up to the 3D structure macro scale level.
So how much time it take for you to finish one run of high fidelity simulation, the multi-scale multi-physics simulation? Is it in days, in weeks, or in hours?
It won't be like a weeks. That's not that complicated. Because that's a reason we want to separate it. We want to separate the solid mechanics model with the electrochemistry model. Then we can save some time. Right now, the most time-consuming part is the electrochemistry model, actually, because that's involve the transport of lithium ions, how that impact, how that change with time during the lithiation and delithiation process, and how that impact by the kind of chemical reaction during the forming of ICI layer. So that's the most consuming part. I think that's a few hours or up to days, but I don't think that will go beyond 2 days. Yes.
Okay, thank you.
Yeah, thank you for your talk. I think it's a very, very interesting physics. You have two phases. The first phase, generate this geometry, and then the second phase, the simulation of this, for each island. So I wonder, have you tried or any comments about the practice of doing surrogate modeling for each phase individually? Well, I understand that there may be some difficulties. For example, that your response in the first stage is actually a geometric, participation. Partition of these, these 2D plane. Well, is there some possibility, for example, you do this for the second stage and combine these, first stage physics and the second stage, surrogate, or this kind of practice, and any thoughts about comparing the result of doing so with the, you're doing this two-stage model, as a whole, and which one will perform a little bit better? Yeah, thank you.
That's a very good idea. I think that's kind of different directions going. You can, because for multi-scale simulation, when you develop surrogate models, some effort has been there for, we can develop surrogate models separately to improve the fidelity of each model, and we can have a way to combine them together. Right now, because I guess right now the Gaussian process model, it's a relatively simple surrogate model techniques we can use, and it's performing relatively good right now for our case. But if we have more, if we need to consider more factors that make the problem more complicated or more high dimensional, the other option is we can do surrogate model for each length scale or each physics model simulations.
Yeah, so in current practice, are you doing individual island simulation, micro-level simulation in parallel, and then combine them together?
That's a very good question. Right now, we are now doing statistic. It's not fully statistic. We are using what we call representative volume element. We just choose the biggest island size, use that assay that can best capture the performance of the battery. Yes.
Yeah, I think lots of interesting analytical questions, deeply rooted in these applications.
Yes. Thank you.
So the battery structure you showed in the first few slides, the internal structure, I guess it will be super difficult to manufacture those structures.
Some of them is if the open what's that? Suddenly I don't have. I forgot the name. For the most simple case that can be relatively easy built, use what we call the sintering process, use some particles. So they can use polymer particles to build the base structure. Then you fill in the silicon on it, and also nickel at a certain level. Then you can remove the polymer particle. Then you can build a 3D structure. That's kind of more controlled power structure. But for some of the structures, yes, that's very difficult to print, especially at the macro scale level. We are able to print some of the structure. Probably it's not the best one. So we are able to print some of the structure, use our like a simple 3D printer, but that's not at the scale that we can test it as an electrode yet.
So do you think the new experimental data, for example, the defects in those structure may affect this framework that you just showed?
Yes, that's for sure. The 3D structure, if we have, but first of all, we want to have a way to have we can explore all different structures, how that impacts performance. Then that will motivate us to really, after building all those structures for high performance battery in the first place. Now we think we have some idea how that can improve, but we don't have a demonstration how much improvement we can gain from such kind of 3D structure. So right now the work is more like we build a tool that we can quantify such kind of influence from the 3D structure, then further motivate us to, after those 3D structure, to really build the battery.
Yeah. For this stress and strain distribution, where does the external force coming from?
That's come from the lithiation process, because the iron will insert it to the silicon crystal structure that will make it expand. Yes.
So when you are doing model validation, the batteries you used are self-manufactured?
You mean for the model validation, the experimental data here?
Yeah.
Right now, we have some data for the 3D structure, but it's not. We see some problem with that data. So right now, it's relatively simple for the thin layer. We just deposit the silicon on the nickel base. Then we change the thickness of it, also changing, let's say, the charging rate or temperature. That's the data right now we're using for. It's mainly for validating the microstructure level model. Okay. We don't have enough data for the whole multi-scale model to be validated.
Okay. And are you using nickel as the substrate because you are directly using it as the current collector?
Yes. The nickel will be the current collector. Yeah, right.
Is it more like a thin metal sheet, or is it more like nickel is being deposited on the surface of something else?
I believe the nickel is a current collector that will be used as directly in the testing, in the device testing.
Yeah.
So you mean where nickel will deposit it? I'm not very familiar with the experimental parts. I lack of knowledge of how the nickel will be fabricated.
Got it. Okay. And what material are you using as the electrolyte?
The electrolyte. So you mean for the experimental testing or the simulation? I think we just use the most the commonly used electrolyte. I don't remember exactly what's electrolyte. It's not a specific electrolyte. It's the most widely used one. Yeah.
Okay, thank you.
Yeah, great talk. I just have simple questions. Do you know what is the industry practice when they design these batteries? Do they use a similar multi-scale simulation to guide the design, or what kind of process they use in practice? Yeah.
In practice, because right now silicon is not really commercialized. Silicon anode is not commercialized because the problem it's people have been observing due to the mechanical failure result from the volume change, but it's quite promising as we see how much capacity can be theoretically increased. That's like draw a big interest in using silicon. That's also kind of why we want to do this work. If we want to move ahead to make it feasible to use silicon, we need to understand all those. How can we mitigate the volume change if we use the silicon as anode? So we are interested in the theoretical predicted performance using silicon, but we want to mitigate the damage that will significantly reduce the lifetime of it. So that's kind of one of the reasons why we want to do the simulation, to get more understanding, to evaluate all the solutions we can use. One of them is 3D architecture to address the difficulties with using the silicon as the anode. But right now, we don't use, silicon is not commercially used as anode.
Any other questions? Okay, if no further questions, let's thank our speaker one more time. And then, today, the SME student chapter, our local student chapter, S133, also prepared some food for everyone. It's outside. So, the president is Wenpo this year, and we are currently actively looking for new members to the SME student chapter. If you are interested in joining the student chapter, you can email me or email Wenpo for that. So, enjoy some food outside. Thank you, everyone.